Hi guys, so this is week 5. This is the first week that we're going to move on from something really other than linear functions. The chapter 1 that we've done is pretty much, even though you had a little introduction to some other kinds of functions on your graphing calculator, everything was linear to this point. So this activity 3.1 starts with a situation where somebody's willing to work for the first day 2 cents, and then the next day you would pay them 4 cents, and the next day 8 cents, and keep going like that. So something that's linear, the increase would be the same amount per day. So we can tell right off the bat that this is not a linear relationship. So the first question we're being asked is, should we hire him? Okay, so I do this question all the time when I am teaching this in a classroom about, is this a good deal? Should you take this job if your boss offers you this? And obviously most people say, no, I would never take that job. So on the hiring standpoint, at the beginning when I look at this, would you hire him? We'd probably say, yeah, it's a great deal. Okay, the worker, he's really inexpensive. Okay, so let's actually look at what happens to this. We're going to look at that chart in a second. So they gave us the first 4 days in that situation, in that paragraph up top on what he's going to make. So now they're asking us, what's he going to make the next couple days? So on July 15th, he's going to make, I'm just going to use an arrow rather than just an equal sign. He's going to make 32 cents. And then on July 6th, he's going to double that again. So he's going to make then 64 cents. And the one thing when you're doing this I want you to keep in mind is what we're getting out is his pay just for that one day. So it's not even including, all the days before. It's not his total pay. It's the day's pay. Okay, so let's look at here what his total pay. Okay, so number 3 is asking us not what's he going to make on July 7th, but what his total on July 7th, the first week. Okay, July 1st through July 7th. So if you add those all up and find that last one, July 7th, he would make $1.28. If you add that all up, so that first week he's going to make a total of $2.54. Okay, so let's look at that table that they give us. Let's complete that. So we have already found most of these values. These are going to be in cents. So I'm not going to use a decimal point because my output's going to be in cents. So he makes 2 the first day, 4 cents, then 8 cents, then 16 cents, 32, 64, 128, and then 256. So that's what he makes each day. So do we notice a pattern on the output value? So it's not that it's the same increase. Now a linear from day 2 to day 4 would reduce to the same thing as 4 to 8, 8 to 16. We would have the same rate of change in between there. But this one, there is definitely a relationship, and we're trying to figure out how do you find the next output. So the first thing we're trying to figure out from the previous day, okay, from day 1 to day 2, I'm multiplying by 2. Then 2 to day 3, I'm multiplying by 2. Okay, so I'm doubling the pay each day. Okay, so for each day, the pay gets doubled. I'm going to write it as multiplied by 2 instead, and you'll see in a second why that 2 is important. Because if it was tripled each day, then that 3 is that common factor that we're looking for. Ultimately, what we want to do is to be able to write an equation that's going to, a model, just like we did for linear functions, that we can find the pay for any day. So is this linear? We already had said that. No, definitely not linear. Whoops. No, there is not a constant rate of change. Multiplying it by 2 each day is not going to give me a constant rate of change because I'm constantly using that previous output and multiplying it by 2, so the output changes by more than that. So what's the practical domain? Oops, I think I skipped one. Hold on one second. The slide was moved up, so I got to just move it a little bit. Sorry about that. There we go. I was wondering why they were asking that so far before we've done other things. Okay, so they're asking us to figure out the next day. So that's really just taking our table The last one that we had on our table was that 256. Times that by 2, so on July 9th, we are going to get paid 512 cents. So in other words, $5.12. That would be our pay then. Okay, so the next thing they want us to do, and this I'm not going to switch back to the previous slide because that messes up the video, but you probably want to turn back and just look at your table and look at all the list of outputs. And if you notice, each one of them, because we have this factor of 2, that we're doubling each day, each one of those outputs can be written as a factor of 2. Okay, so on the first day, they're helping us do, so on the first day, I get paid 2. Okay, so let me actually do this. There's the first day. On the second day, my output was 4. On the third day, my output was 8. So each day, if I take 2 and raise it to the day that I'm on, that's where I'm getting my output. Okay, so you can check it. We could do the next one over there. If we did 2, that we just did 2 to the 9th, we test that, we better get 512. So what we just came up with is this function where if I take 2 and raise it to the nth power, n being the number of days that we are into July, that's, whoops, let's get rid of that little, that's our function. Okay, the 2 is in there because it's doubling each day. So if this were tripling each day, then it would be 3 to the n or 3 to the x, depending on what variable you're going to use. So that's what we call an exponential function. Okay, and it's exponential not because there's an exponent in it, but because the variable is in the exponent. And this is the first time that we've seen that. Okay, having x to the second is much, much different than having 2 to the x. So if something doubles each day, that really means that it's what we say growing exponentially. Okay, because each time it grows, it's growing faster and faster. So now the next thing they want us to do is to use that function to find p to the 20th, or p of 20, I should say, which is the same as 2 to the 20th. So this is on the 20th day of July. If you figure that out in cents, we get 1,048,576 cents. Okay, so when I turn that into dollars, I ran out of room on that. Oh, let me just move this over a little. There we go. When I turn that into dollars, okay, just move my decimal point twice, I get $10,485.76. So I just want to keep reminding you that that is just the pay on July 20th, not even including any of the days before. So 20 days in, if I start with 2 cents and double it each day, I'm at $10,485. So it's crazy how fast that, just starting at such a tiny amount, if it's growing exponentially, how fast it grows. Okay, so the next one, they're asking us to do the same thing. P of 31. Okay, so 2 to the 31st. So when you end up doing that out, I'm just going to go right to dollars. This is 21,474,836.48, which is crazy, obviously. Okay, that is on July 31st. Again, not including all the days before it, just for that one day. So really, was it a good choice to hire him? At first, it looks like, oh, super cheap. It's going to take forever for that to get big. But no. Costs too much. So you want to pay that person a flat rate each week. You don't want it to grow exponentially. Okay, so I kind of, just going to kind of gloss over this a little bit, because they're trying to, I already answered part C by accident before. They're asking us to figure out what is the change in from 3 to 4 days. And if we look at our table, from 3 to 4, we made 8 cents per day. Day 3, I made 8 cents. Day 4, I made 16 cents. And if we do the same thing between 7 and 8, the rate of change is 128 cents per day. So we can see right there, we knew from our table, we can tell from our equation that we already wrote, that this was not going to be linear. But there we just kind of showed that it's not, okay? So we don't have a linear relationship. So in this question, what's the practical domain? Remember, practical is what's going to work just for this problem. So this problem is just talking about the month of July. So we would only use n's from, so n could be anywhere from 1, the first day, to 31, just because this is 31 days in July. So I actually did the scatter plot ahead of time just to kind of show you. So I didn't plot everything because we wouldn't have enough room, obviously, to go past a certain number of days. Even when I'm getting to day 10, it's getting pretty high. So there's my scatter plot. And you notice it doesn't look linear. If you're not careful, it may look linear, but this actually looks like a curve. So it kind of starts off slower, but then it grows pretty fast after that. Okay, so the next graph right here, discrete or continuous. So it depends on if we're talking about this function in general. Like if I just gave you the function 2 to the n, that's much different than the one we're working with that's only talking about the days of July. So in this case, this would be discrete because there are a finite number of days in July. Okay, if I was looking at just 2 to the n with no background or anything like that, then that one would be a continuous, because I can plug in anything that I want for n there. Okay, it's defined for everything. Okay, so we already talked about that this is called an exponential function. And so the general form of an exponential function is right here. Okay, where b is greater than 1. Okay, because that means that this is going to be growing exponentially. You'll see, this is kind of, what do they call? They call this different things, but this you're going to see down below that b is what we call our growth factor. And we can see what happens if b becomes less than 1. It doesn't start growing, it starts decreasing, it starts really depreciating. So when you see things like cars, a lot of times they depreciate really fast at the beginning and then it slows down. So that's still an exponential function, but it's not growing, it's decreasing. Okay, so the next things they want us to do, let's see. Graphs of increasing exponential functions. So what we just had was definitely an increasing one. Okay, and the next thing they're going to have you do is plot that. Okay, sorry about that. I had to pause the video for a second. So they want you to graph this one on the graphing calculator. Okay, so the way you use the exponent is that you just use that caret. You can use that for any time you're raising to any power. And if you look at that graph, you'll see that it is continuous. There's no holes, no gaps, no breaks. So when I'm looking at that one, rather than the practical domain, the actual domain for this one, so my domain would be all real numbers. This is good for any value. And if you look at the range, if you look at the y's on that graph, let me see if I can just move over a little bit to find it. Where is it? Oh, okay. You know, I actually thought that they showed you that output, so I'm just going to do a quick little sketch over here. Oops. Okay, so the actual sketch of the graph looks something like this. Okay, so it does increase fast, and then it starts to, on that one, it starts to level off. Okay, actually a little bit closer to the y-axis, but the domain is not all real numbers. For this one, it's never actually going to reach 0. So it kind of approaches it, but never gets there. So my range is also all real numbers. Okay, so they're asking the next thing is what's the y-intercept? So the y-intercept you're always going to find by plugging 0 in for x. So if I do that, now 2 to 0, anything to a 0 power always comes out to be 1. So that's right here. That's my y-intercept. And this one happens, this is an increasing function all the time. Okay, so you'll see if b were to be, say, a half, okay, then that means that this would be a decreasing function. And you look at a lot of things like that when you talk about half-life. If you've taken any science class that talks about like the half-life of caffeine, that is a decreasing exponential function with not a growth rate, but it's a, I'm not sure if it's called depreciation rate, but it's when b is less than 1. Okay, so they're just telling us here about that growth factor.